Next, we have a beam question. The figure shows a tapered elastic bar of length L subjected to a tensile load P at the bottom end and a fixed support at the top end. The cross-section area varies from A0 to A0 divided by 2 at the bottom end. Calculate the displacement at the bottom end by part 1, modeling the bar as a single bar element, and part 2, using two bar elements of equal length. Take the cross-sectional area of the bar to be equal to the actual cross-sectional area of the taper bar at the mixed sections. So basically, this problem says that we have this real bar. Okay, a bar is a structure that supports axial loading. Okay, it supports axial loading in static conditions. So here we are applying axial load. Right? Axial means it follows down the axis of the beam. Okay, so here is the real thing, and these two are the models, the FEM models. Because it's tapered, okay, tapered means its cross-section area varies, right? You see it's wide here, but towards the bottom is a smaller cross-section area. So that's what it means by tapered. So there are two ways to model this. One way is to take the average cross-section area and then model it as a bar of constant cross-section area. And that area happens to be the average. Whereas the other version is to make a step, what do you call this? Bar, okay, a stepped bar. So one step has an area of 7 over 8 A naught. And then the second step has a cross-section area of 5 A naught over 8. Okay, so we're asked to find the displacements. So this face, how much does it displace? Okay, so in other words, for part 1 we're asked to find U2. For part 2 we're asked to find U3. Okay, so how much does the bottom face displace? So let's start with part 1. So part 1 we are focusing on this diagram, right? So you see the model, the FEM model, has two nodes, nodes 1 and nodes 2. And then this has U1 and this has U2. And also don't forget the loadings. So the loading here is, we can call this let me see what name did I give it. Okay, just call it F1 and F2. Okay, so what formula do you use for beams? If you look at the lecture notes, the element matrix for beams, sorry, this is not a beam, this is a bar, is this EA over L divided by 1 minus 1 minus 1, 1. So it kind of looks like a spring element. Yeah. In fact, since this is the only element in this matrix, this is the only element in this model, we can straight away write the global equilibrium equation. The global equilibrium equation here happens to be just this element matrix. Okay, so we can straight away write this as the global equilibrium. So you see down here, we apply a force P. Okay, that's why uh, F2 will be replaced by P. Okay, so I will straight away substitute P here. And then here, well, there's a wall, right? And there's a ceiling. A ceiling will exert a reaction force. Okay, so that's why we will substitute F1 with R. Okay, so this will be R. Okay, I call it R1 to denote that it's a reaction force at point 1. So what is A, what is E, what is L? E is the Young's modulus of the beam, the bar. A is the cross-section area of the bar, and L is the length of the bar, or at least the length of the bar element. So you see it's said to have a length L, so we can just keep L as it is. In this model, the cross-section area is 3A naught over 4, right? So let's substitute that in. So instead of A, this should be 3A naught over 4, right? If you simplify this, okay, it'll be 3 A naught E over 4 L, 1 minus 1 minus 1, 1. And then here we substitute the boundary conditions. So we know that point 1 is fixed, right? So that means U1 is equal to 0. U2 is unknown, is in fact what we want to find. Okay, because this has a 0 displacement boundary condition, we can eliminate it to get the reduced system. Okay, so the reduced system says that okay, the reduced system states that this times this times this will be equals to this. Okay, 3 A naught E over 4L U2 is equal to P. So U2 is our unknown, right? They asked us to find the displacement at the bottom. So U2 is equal to 4PL over 3A naught E. Now, why did the answer say 1.333? It's because if you calculate 4 over 3 into, if you put 4 over 3 in your calculator, you get 1.333. Okay, so that's how they got that answer. Okay, now let's move on to the second question. The second question states, uh, the second question is a step model now. Okay, so now question 2 is like this. So we have 1, 2, 3. This is U1, U2, U3. Okay, so for element 1, so this is element 1, this is element 2. So element 1, we need to write down the element matrix. So the element matrix is 1 minus 1 minus 1, 1. Here we substitute in the Young's modulus, then the cross-section area, which is 7, 8 A naught over 8. Divided by the length. In fact, the length is half of it, right? Yeah, of equal length. So it's just L divided by 2. So actually, this shouldn't be L, this should be L divided by 2. Yeah. So, okay, we don't need to write this side. It's not important for now. What's important is only the stiffness matrix. So if you simplify this, you will get 7A naught E over 4L 1 minus 1 minus 1, 1. Now we look at element 2. So element 2, again, the Young's modulus, the cross-section area this time is 5 over 8. Yeah, 5 over 8 A naught. This times 5 over 8 naught. Divided by, again, L over 2. Then 1 minus 1 minus 1, 1. If you calculate this, you should get 5A naught E over 4L. Oh, I forgot to label the rows and columns. Okay, so you need to label the rows and columns with nodes, right? So for element 1, the rows are, sorry, the nodes are 1 and 2, right? So that's why I label here 1 and 2, 1 and 2. And then for element 2, the nodes are 2 and 3. That's why I'll label this as 2, 3, 2, 3. Okay, so this will help us combine them later in the global equilibrium matrix. Okay, so now the global equilibrium matrix. Okay, but I want to tell you an additional step first. So before we combine them in the global equilibrium matrix, right, what I want you to do is take this 7 over 4 here and then multiply it into each entry of the matrix. So at the end of the day, what you'll get is this. So this is 7/4 minus 7/4 minus 7/4, 7/4. Okay, you do the same thing with element 2's matrix. So you take 5/4 and then you multiply it into each entry of this matrix. Okay, so at the end of the day, this is a 2, 3, 2, 3. Yep. So now you can write the global equilibrium equation, global. So because there are 3 nodes, we have a 3 by 3 matrix. Then, okay, the reason why I multiplied this in, right? I multiplied the 7/4 in and the 5/4 in is that when you look outside of the matrix, see, they both have a common factor of A naught E over L. Okay. Now both the element matrix have a common factor of E naught E over L. But if I didn't multiply in that 7/4 and the 5/4, they would be different, right? So the reason why I multiplied the 7/4 and 5/4 into the entries is because now they have a common factor of A naught E over L. So that's why I can put that outside. Okay, then you can combine them into the global equilibrium matrix. So you see for element 1, we had to focus on row 1, column 1, row 2, column 2, and fill it up with 7/4s. Okay, whereas for element 2, we need to fill it up. Row 2, column 2, row 3, column 3 with 5/4s. Okay, so yeah, that's it. So in fact, in the middle here, we have 12/4, which is actually 3. Okay, I'm gonna straight away. Never mind. So this is U1, U2, and U3, right? U3 is the unknown that we want to find. Now, what are the loading conditions? Well, node 1 is fixed to the ceiling, right? So there's a reaction force. This should be R1. U2 has no loading. Okay, so that's why you put it as 0, right? I'm not pulling at node 2. Okay, so that's why U2 is 0. And then U3, sorry, node 3 has the force P applied onto it, right? I'm talking about this force P. Yeah. Now we need to look at the boundary conditions. So again, node 1 is fixed to the ceiling, that's why it's 0. Okay, so that's why this can be 0. And then U3 is unknown, U2 is unknown. So because row 1 has a 0 displacement boundary conditions, we can eliminate row 1, column 1. Yeah. Okay, so now our reduced system is just row 2 and row 3. So A naught E over L. Here we have 2 and 3. This is 3 minus 5/4 minus 5/4, 5/4. This is U2, U3, 2, 3. This is 0p. Okay. So we're interested in U3, right? We're interested in U3. That's why okay. Then what we can do is we make this displacement vector the subject. Okay. How do you do that? Okay. First thing you do is we move this to the other side, right? Well, actually, we can do this all in one shot. So what I mean is, okay, this one will become. So if you move the matrix to the other side, it will get inverted. Then if you move this factor to the other side, it will become reciprocal. Okay? And actually, right, you can treat this vector as having a common factor p, right? 0 is the same as 0p. So I can actually pull out a factor of p from this displacement vector. Okay, so this will become 1. Then I can bring the p outside here. Okay, so I just factorized out p. And what's the advantage of doing that? Well, I can just press this into my calculator, right? And then you should get 4/7 and 48/35 PL A naught B. Okay, so that's U2 and U3. But what we're interested in is actually U3. So look at this. U3 is actually 48/35 PL A naught E. Okay, so that means U3 now, if you punch this in your calculator, it will become 1.371 PL A naught E.